Hello and welcome to Empowered Learning. This video will be the introductory video to first order ordinary differential equations. And the things that we'll study here is how to recognize a directly integrable ODE versus an autonomous one versus what we're going to call a separable ordinary differential equation. We also want to talk about whenever we have constant, or sometimes we call them equilibrium solutions, whenever we have first order ODEs. We will see this whole thing of constant solutions come up again whenever we start to study higher order ODEs as well. But we do an introduction to that here. And we also want to make note of the existence and uniqueness properties of initial value problems for first order ODEs as well. And so we'll kind of see these existence and uniqueness properties change, but yet be similar whenever we study higher order ODEs as well. So up to this point in our study of solving ODEs, we have just encountered solving for general and particular solutions of directly integrable ODEs. And so we did this. If you are watching the videos in succession that I've done, that was in the chapter 2 video, okay, or the one that was about directly integrable ODEs and using indefinite and definite integrals to be able to solve initial value problems of that ODE type. So in general, whenever we are dealing with those types of ODEs, we're dealing with first order ordinary differential equations. A lot of times where we see that our equation ends up being the first derivative of some function y is equal to a function that is both in terms of x and y. Okay. Now, in summary, we'll see these three types of first order ODEs a lot as we learn to solve more differential equations here. Okay. Now, the main thing that I want to get across here is being able to recognize these three different types of first order ODEs. So, of course, the directly integrable ones, we see that we basically have the derivative of some function y with respect to x. And of course, this variable and the independent variable for the function is the same. So here we see that the derivative of y is only a function of x. Okay. When we have autonomous equations, we see that the function that's on the right side is defined in terms of the actual function y itself. Okay. And of course, normally, we'll just keep it, as y for short. But we'll have some function of whatever this is on the right-hand side of the equation. We call this separable because if we do the math for this, I could separate or rearrange this equation in such a way to where I would have everything in terms of x on one side and everything in terms of y on the other. And to be specific about it, I'm just going to come up here and do it. I could take this particular equation and rearrange it this way to where I have dy over g of y, and that would equal to f of x times dx. And so here, I could, of course, look at the left side of this as g raised to the -1 of y dy, where this would still just be some function of y here. Here is just a function of x. And then, of course, you got your dy over here and dx there. And so by us being able to take this particular equation and rewrite it in this form that I've mentioned here, and I'll just rewrite it here for clarity, I could actually take this situation here, and if I wanted to be able to solve this, I could just do an indefinite integral to both sides of that equation, and provided that both g raised to the -1 of y and f of x both have antiderivatives that are elementary, I could actually solve this particular differential equation. Okay. Now, the video that I'm going to make on separable equations and solving those examples is not going to be this one. It'll be another one that I'll make after this one. But of course, in this particular video, I just want you to recognize the three different forms. And so I just want to make sure that that's clear. All right, so let's move on. So again, I'm saying it's important to know and recognize the different forms of ODEs in this course, as recognizing ODE forms will guide you in letting you know what techniques and or other special considerations you need to think about in the process of finding solutions to ODEs. So to put that in short, when you're studying differential equations, the whole idea is to say, hey, what type of equation is that? Once I know what type of equation it is, I know what tools I can use to be able to solve it. Okay, so that's essentially what the whole game is. The deeper that you get into a differential equations course, the only thing that's really different is that now you have more equations to recognize and more tools to remember. So that's pretty much it. All right, so let's go through an example here of looking at several different types of ODEs, and let's see if we can actually recognize if they are directly integrable here, or autonomous, or neither, meaning neither autonomous nor directly integrable. Okay. So for this first equation, if we look at it here, and for all these examples here, the first thing that we want to do is get it into this form. Okay. After we get it into this form of dy over dx is equal to some function of x and or y, we do whatever simplification we need, and then we answer the question. So for here, I could divide both sides here by x. And if I did that, I know that these x's here would reduce to 1. And what I would essentially have here is dy over dx, which is 1 over y. And of course, with this initial condition here. Now, the initial condition part is not important. What is important is this portion here. And if you notice here, I have dy over dx is equal to strictly a function of y, or strictly a function of the function I took the derivative of. So in that case, this ends up being an autonomous type of function, or an autonomous type of equation. Because again, if we look up here, remember that dy over dx is equal to some function of y. And just to make this clear, if I had dx over dy, and if this function, or if this equation was equal to f of x, this is also considered to be autonomous as well, because whatever the function I took the derivative of is actually the independent variable for the function on the right-hand side. So it's not always going to be, defined in terms of y. It's just, is it defined in terms of the actual function that we took the derivative of on the left side. Okay. All right, so let's look at the next one here. So for this next one, of course, I could rewrite this as just dy over dx is equal to square root of 1 minus y, all that over x squared minus 1. And this indeed is just a function of x and y. No way I'm going to be able to simplify this. So in this case, this would be neither. Okay. For this third example, note that I could take this equation and rewrite this as 6 plus 2x, all that divided by x cubed. And notice here that this is just a function of just x. So I have dy over dx is equal to a function of just x. So this one is going to be directly integrable. And I'm just going to put di for short. For the next one, if I was to rewrite this, this would be dx over dy. And this would be 8 minus 5y, and I'll take that and divide that by y squared minus pi. And so notice here that I have dx over dy, okay? So y is the independent variable here. And so my function on the right-hand side is defined in terms of the independent variable here. So because of that, D is acting just like C is. So this would also be directly integral. So for example E, I could rewrite this as du over dy is equal to 10u squared minus 3 plus 6u. And all of this is defined as a function of u, same as what this is up here. So this would be an autonomous function. Okay. So for f, we see that there's nothing that we need to do to rearrange anything, but we see that what we're looking at here is a function of z and y. And of course, my function that I took the derivative of here is of z. So this would be a case where it's not going to be autonomous and it's not going to be directly integrable. So this would be the case where it is neither. For g, we could simply rewrite this as adding dy over dx to both sides. So literally, we could just kind of get rid of this, add it, and it'll end up looking like this. And we see that this is really a function of y. And so dy over dx equals function of y. That would be autonomous. Okay. And so for our example h, if we were to divide both sides by x squared here, then of course this would go away on this side. We'll have x squared down here in the denominator. And of course, if we simplify, this would just be negative y divided by 2x. And of course, this is just a function of both x and y. So because of that, this would be neither autonomous nor directly integral. And in this last example here, of course, we could rewrite this as dy over dx is equal to minus x over y to the fourth divided by absolute value of x. Now, since we're told here that x is going to be positive, we could rewrite this as just rewrite absolute value of x as just being x. And so this is just going to be x. And of course, this x and that x will reduce to 1. It'll just end up being negative y to the 4, which is just a function of y. So dy over dx is equal to f of y. That ends up being autonomous. All right, so we've gone through a lot of examples of being able to recognize when a first order differential equation is autonomous, when it is directly integral, and when it's neither autonomous nor directly integral. Okay. Now, again, the reason that we want to do this is because for a directly integrable type of differential equation, we already know how to attack solving that particular type of differential equation. Okay. Whenever we have an autonomous differential equation, there's other things that we need to consider, like do we have any constant solutions? And so that's why we're actually introducing the whole notion of what an autonomous ODE is, because whenever we recognize we have one, the first thing that should pop up in our minds is hey, do I have a constant value that I can plug in for y that would make my derivative go to 0, or would it satisfy would it actually satisfy the differential equation? Okay, and we're going to look at that here in just a second. So constant, or what we call equilibrium solutions. So we have a constant solution to an ODE is just a constant function. So something like y equals 2 or y equals -8, where the constant c, of course, is just a real number. Okay. Now, if we look at this, if I say that, let's say y is equal to 5. So let's just say that. So let's say y is equal to 5. And I have some differential equation here. dy over dx is equal to, let's just say 5y, something like that. Okay. Or sorry, let me not do that. Make it a little bit more simple. Let's just say it's equal to 0. Okay. So here, does this particular function satisfy this differential equation? Well, we know that it does. And the reason that we know that it does is because we know that the derivative of any constant is going to be 0. Okay. So if we had a derivative of any function and this result here on the right side ends up equaling 0, then we know that any value of y, any real number value of y will do. Okay. But sometimes, of course, we have situations where our derivative of y with respect to x ends up being something different, like this. And so in these cases, we need to figure out, all right, well, what values of y do we have here will actually produce this same thing of dy over dx is equal to 0. Okay. And so if I can find values of y that I can plug in, let's say here and here, that make this entire expression equal to 0, then of course those values of y would satisfy this particular equation here. Because again, we know that y in and of itself, if I took the derivative of it and it's a constant, is going to equal 0. But I also want to make sure that it satisfies this as well. Okay. Now, in this particular example here, and I'm going to erase this so that we can see this clearly. So in this particular example, I tell you that we have two trivial solutions. Well, we have one trivial solution, which is going to be y is equal to 0. And we have a non-trivial solution, which is going to be y is equal to 3/4. Okay. Now, we say trivial whenever we're like, yeah, I can just look at it and tell that this is going to make my whole thing go to 0 here. So for instance, 0 is an easy number to plug in. If I plug in 0 here and 0 here, then 0 times anything is 0. 0 times anything is 0. So of course, if I let y be some constant value that's equal to 0, then of course the derivative of 0 is 0. Okay, so that's why it's considered to be trivial. Now, the non-trivial solution is something other than y that equals to 0 that acts the same way as y equals 0 does. Okay. And so down here, I've actually went ahead and worked this out so that you can see why this actually works out. So again, we're trying to find values of y that make the right-hand side of this particular differential equation here go to 0. Okay. And of course, we see that if I was to plug in y equals 0 and if I plug in y equals 3/4, both of those real number constant values for y would actually work. And so for this first one again, we easily see that, hey, if I let y equals 0, then the derivative of 0 is 0. And then if I was to plug in 0 in for y both here and here, it still ends up being 0. So that means that whenever y is equal to 0, all of this is going to be 0 as well. Okay. Do the same thing for 3/4. So the derivative of any constant is 0. So it satisfies that. And of course, if I plug in 3/4 for y here, I see that I still end up getting 0. And of course, this expression here is what was on the right-hand side of my original equation here, okay? So that is the definition and an example of what a constant solution actually is. And so again, to reiterate, we know that for some constant value, we know that the derivative of that constant value is always going to be 0. And so if we define the derivative of some function y as something else, we want to know, are there any constant values c that we can plug into it so that we end up getting 0 here on the right hand side. All right. Now, if we look at the case where y is equal to 2, we'll see that this is not actually a solution to this particular differential equation, because although dy over dx is equal to 0 when y is equal to 2, if I was to plug in 2 here and plug in 2 here, what I would get is 3x squared, or sorry, 6x squared, because 3 times 2 is 6. So let me fix that. So I would get this here, and then of course, 2 squared is 4, and 4 times 4 is 16. And notice here, this would end up being 10x squared. So I would have a situation here where this does not end up equaling 0. And the only way that a constant value here for my function y ends up being a solution for it is that I have to be able to take the derivative of this and get 0 and plug that same value into whatever the derivative is equal to, whatever expression I make it equal to, and it's still equal to 0, okay? Now, it's possible for our ODEs to have either only constant solutions, like what we saw in our very first example, only non-constant solutions, and we'll see a lot of that as this course goes on, or we can have ODEs that have a combination of constant and non-constant solutions, okay? So many of the ODEs that we deal with in our study of the body, in this body of knowledge, will be the type that does not have any constant solutions, okay? So as we get deeper into this course, we're actually going to see that. However, we will now show an example of an ODE that has both constant and non-constant solutions. And I'm doing this so that you can kind of see the difference in between the two, okay? We've kind of already seen something like this, but I wanted to be very clear, so I just did a separate example for it. So we want to consider this particular first order ODE. Now, for this particular first order ODE, we're assuming that we have a function y that's going to be a constant, okay? And what we want to do is find the value or values of this particular constant that will satisfy this particular ODE, okay? Now, to be clear on this, if I am using a constant value for my function here for dy over dx, then notice that the derivative of any constant has to be 0, okay? So what that means is that whatever f of x and y, and of course this function defined in terms of x and y, whatever it ends up being, if I plug in y equals c into it, I still have to get 0 as well, okay? Now, in doing this, the first thing that I need to do is rewrite this particular first order ODE so that I have it into this form of dy over dx is equal to a function of both x and y, okay? So essentially what I do here is I'm going to add this term to both sides, subtract that term from both sides, and I have it here. And then since this on the right-hand side is a 4-term expression, I'm looking to see, can I do factor by grouping here, okay? And I see that with these first two terms, they have in common y squared. Second two terms, they have in common a -4. So I go ahead and I factor that out of this first group of terms here, second group of terms there. And then from here, I see that I just have y squared minus 4 and x minus 5y, okay? Now, if I want to know what values of y equals c, where c is a constant, that's going to produce a solution to this particular differential equation here, I have to look at what values of y here make this particular factor of this expression here on the right go to 0, okay? I do not look here for constant solutions, okay? I only look here for constant solutions. Now, if I was just looking for solutions in general, then of course I would consider this other factor, and I would say whatever it is, okay? Now, if I keep on going with this problem here, notice that if I'm assuming that y is equal to some constant here, then the derivative of any constant should equal 0. So that's why I have that there. If I let y equal c, then I plug this in, and then from this point, it's just a matter of solving this particular equation. And of course, this means that c squared minus 4 is equal to 0, or x minus 5c is equal to 0. Once we work all that out, you see that we have c is equal to plus or minus 2 as our constant solutions. And of course, c being 1/5 x will be a non-constant solution, okay? Now, even though we said this was going to be a constant number here, I've wrote this out explicitly so that you can see that here, in order for this to be a constant number, I would have to know what x is. And since x could be anything, I can't really consider this to be an actual constant solution, okay? So that's why for this particular example, we ignore that particular case, okay? And so hence, this is why I say that y equal to being plus or minus 2, and y is equal to 1/5 x are the three solutions to this ODE. However, these two solutions are the only ones that we consider to be constant solutions, okay? Again, since x could be anything, I can consider 1/5 x to be a constant solution. And so that ends up being our answer here. Now, the note that I put here just simply states that one thing that I could have done here, instead of just kind of breaking this problem up, is I could have just went in exactly and said, well, let this be c, let that be c, let this be c, and do all the rearranging and factoring that I did before and figure out the answer, okay? But again, I wanted to kind of formally go through it so that you understood the difference in between a constant solution versus a non-constant one. The main thing here is we're looking for constant values for y that make our derivative of y with respect to x equal 0, okay? That is what we're looking for. We do not consider what values of x could be to make our derivative 0. We don't care about that, okay? Only what the actual, if the actual function is a constant and it makes it go to 0, we count it, okay? So in our last example that we had, one of the things I wanted to point out was that if we, for this particular differential equation, with this results here, we can technically call this an initial value ordinary differential equation because of the fact that y of x, where any value of x will do, will be equal to plus or minus 2, okay? It can also be interpreted as a separable equation as well because of the fact that it's constant with those initial conditions. So what we want to know now is how can we determine if an initial value problem type of first order ODE actually has the potential to have at least one solution without having to actually go through this whole process of solving for these solutions first. Okay. So if you notice, in order for us to figure out if we had any solutions and to figure out how many, we've actually gone through and went through a whole process. So, but there is a way for us to be able to know if we're looking at a first order initial value type of ODE, to know whether we're going to have at least one solution before we even begin trying to solve for it. Okay. And in mathematics, this is an important thing because we really don't want to waste a whole lot of time on something that we know, hey, there's not going to be a solution for it. So it's kind of like, hey, if this doesn't have the environment necessary for me to be able to find what it is that I'm looking for, I'm not going to go search there. Okay. And that's kind of what the existence and uniqueness theorem for first order initial value problem, ordinary differential equations, is all about. Okay. Now, I'm going to mention this theorem, kind of give you the overview of what it was really trying to ask. And then after that, I'm just going to move on. This is more theoretical, and you don't necessarily have to know this in detail to be functional in an intro to differential equations course. But I do have it here just for some level of rigor to try to establish what it is that we're going to be talking about when we move forward here. So the existence and uniqueness of first order initial value problem ODEs. So if we have an initial value problem of this type, basically a derivative of some function y with respect to x is some expression of both x and or y, and we have some initial condition here. We know that it's going to have exactly one solution on this x value interval, basically in between these two values a and b. So basically, if I have if I'm looking at all my x values here, I know that it's going to be exactly one solution on this open interval from a to b, where whatever x sub 0 is, whatever this value here is, it's going to be in between a and b. I know that. And so we know that we're going to have exactly one solution if we meet the following two conditions. So first, this function here that we said dy over dx is equal to, in this multivariable function in that sense, we have to be able to know that that function is going to be continuous over what we call some open region in the xy plane. Okay. And so this is just a fancy way of expressing what that region looks like. Now, in short, what does that region look like? It looks like a strip in the xy plane. So if you look at an xy coordinate system and you take a strip of it, going up here to positive infinity, here down to negative infinity, but bounded on the left and right by a and b, then we're just considering all these points that are in here. Okay. And that's pretty much what all this is saying. So we have to know that whatever it is that we're dealing with here, this multivariable function, it has to be a function that's going to be continuous within this range here. So all along the strip, I got to have something that kind of looks like that. Now, the second condition is that if I take the partial derivative of this particular two variable function, and I take the derivative of it with partial with respect to y, that also ends up being a continuous function on this same strip here that I was talking about. Okay. Now, why is this important? Okay. Well, in summary, the translation of this theorem is that if I know that this particular two variable function can be expressed as a derivative of y with respect to x, knowing that y at x is a constant function, then I know that, one, this particular function here will be reasonably well behaved within that strip that I was talking about. Okay, so that means that we're not expecting anything out of the ordinary. So we're not going to have a function and then miraculously for some x value in between a and b not have a function. So we're not going to have any ambiguity type things going on there. And number two, we know that y(x) is going to be the only solution for this initial value problem if we have this initial condition here, okay? And of course, we're considering that this is going to be some constant function here. So whatever it is going to end up equaling that value there, okay? Now, just to kind of give you a real simple, quick example to show you how we actually apply this particular theorem, I will go ahead and go through this. If this is something that you're not necessarily interested in knowing, you can just skip this part and go to the next portion of this video where I start to work the examples, okay? But I am going to take a little time to go ahead and do this. So we want to consider this differential equation that we just got through working on, and we know that we could rewrite it this way, okay? And so we're going to look at it from this standpoint here. So we want to show that this particular differential equation here is going to meet the existence and uniqueness theorem conditions to say that, hey, if I had an initial value problem with it, I could actually say that this particular differential equation has exactly one solution to it, okay? So if I look at this, the first thing that I have to show is that this function, two variable function here on the right, is going to be continuous in the region of interest for our given ODE, okay? And so in this case, I don't have, if I look here, I don't have any x value or y value for where this particular two variable function will become undefined, or there's some kind of vertical asymptote or anything like that. So what I'm going to do here is consider the whole xy plane here, okay? So that would be our region of interest. So the first thing I have to do is show that this particular function here is going to be continuous over the whole xy plane for this example. The second thing is if I took the partial derivative of this with respect to y, I need to show that that result also ends up being a two variable function that will be continuous over this same xy plane here, okay? Now, for the region of interest, of course, this is the fancy way of basically saying that I'm considering the whole xy plane. And notice that if I look at this, there is no value of x or y that I can plug in here. That's a real number that will make this expression not be a real number as a result, okay? So there's no combination of x values and y values of the real numbers I can plug in here to where I would get something like a number divided by 0 or square root of a negative number. So for that case, I don't have any situation or any combination of x and y values where my derivative would be undefined or does not exist, if I want to use a proper term for it. So because of that, we know from first year calculus that anytime I know that the derivative of a function exists, then that means that the corresponding function that I took the derivative of for it was a continuous function, okay? So to put it another way, if a function is continuous at a particular x value, I can take the derivative of it at that particular x value, okay? But the converse of that statement isn't always necessarily true, okay? So just because a function is continuous doesn't necessarily mean that I can take the derivative of it. But if the function, but if I have a situation here where I know that my function, if the derivative of the function exists, then I know that the function was continuous, okay? So again, I'll say that again. So if a function is continuous, that does not mean that the derivative of this particular function exists, Doesn't always happen. A good example of that is an absolute value function. This function is continuous, but we know we can't take derivatives at corners. However, if I know that the derivative of some function exists, then I know that the corresponding function that I took the derivative of had to be continuous. Okay, and so that's what I'm trying to get across here. Now, this particular sentence here, the first year calculus statement that I made here, actually proves that first part here, or we actually end up showing that first thing. So when we say we must show that big F of X and Y has to be continuous on the region of interest, we basically took care of that. So now, if I was to take the partial derivative of F with respect to Y, and that's just taking the derivative of this expression where X is going to be treated as a constant, and I'll take the derivative of everything with Y in it as normal. So if I did that, then of course I would get this expression here. And if we look, this expression, there is no combination of X and Y values that I can plug into X and Y to where I'm going to get something like 1 divided by 0 or square root of a negative number. So any combination of X and Y values I plug into here will actually give me a real number. So again, the derivative, a partial derivative of big F with respect to Y will exist for any combination of X and Y values. So once again, I know that since a derivative exists, then that means that the corresponding function F in this case is going to be continuous. Okay. Now, why are we talking about all this? Okay. So basically what we've done here is we said that for this particular differential equation, in the way that it was set up, okay, this differential equation has the environment available so that if I had an initial value problem here, okay, if I had an initial value problem with this setup here, I know that this particular problem would have exactly one solution. Okay, that's the whole point of it. If I see my differential equation, it meets these two conditions, and I know that I got an initial value problem. In other words, I know, let's say, a point on the graph of that particular function, then I know that it's going to have exactly one solution to the differential equation. Okay, and it seems like we're just kind of going down the rabbit hole right now, but this concept is very, very important because as we start to deal with more initial value problems, especially whenever we start to deal with second order and higher ordinary differential equations, it's going to be very important for us to know and recognize that, hey, when we have differential equation with an initial condition and everything is sort of acting well behaved like what we said here, and we just kind of define what that meant explicitly, we know that we're going to have exactly one solution to that particular differential equation. Okay. All right. So enough on that. So let's go ahead and move forward here. I'm going to start working some examples. Okay. Now, the first few examples I have already worked out just to kind of give you an idea of what this looks like. The last few examples I'll actually work live. So for this first example, we want you to rewrite each of the differential equations that we give you so that it's in this form. And again, the reason why we want you to rewrite it in this form is so that you recognize whether it's going to be directly integrable, autonomous, or neither integrable nor directly, neither autonomous or directly integrable. Okay. Now, with this first example here, to make this dy over dx equals something, we see that we can just subtract y cubed from both sides. In this particular case, we see that this is just going to be a function of y. So one of the first things that we want to do here is, since it is autonomous, one of the things that we know is that, hey, this thing has a potential of having a constant solution as one of the solutions for this differential equation. Okay. Now, of course, if we let y equal c, representing some constant, and then we go ahead and solve for that, 8 minus c cubed is basically just going to be the same thing as c cubed is equal to 8. I kind of take the long way of doing it, but that's essentially what it ends up being. And then from here, if I take the cube root of both sides, I see that c ends up being 2. Okay. So this would be a constant solution for this. And I'm going to be more exact here. Is going to be a constant real valued solution for it. Okay. Now, part of the reason why I say it is a constant real value solution for it is because we know that this particular expression here could actually be factored to where we would have two complex conjugate solutions for it as well. But we're not considering complex numbers in this case. We're just considering real numbers. And so this would be the only real number that would satisfy this particular equation, so that if I had a constant value, the derivative of that constant value would be 0. And I'll put it like this: the f of y would also end up 0 if I let this value here be c. Okay. Now, in our next example, of course, if we take this particular differential equation and we rearrange it to have this equal dy over dx, we see that dy over dx is just sine of x plus y divided by y. In this case, if I was to let y equal c, and here I know that if y is equal to c, then the derivative of this would have to equal 0. Okay. And so if I looked here, then I would have this situation here, and I would have to find values of c that would satisfy this equation, where of course c would not be able to equal 0, because if I had that, then that would make this whole expression on the right be undefined. Well, if I was to do that, then of course I would have to consider that the numerator is equal to 0. And of course, we know that for sine, we know that sine is equal to 0 only whenever we have integer multiples of pi. Okay. And so that's why we say that the angle that's on the inside here would have to be an integer multiple of pi. And if I was to solve this for c, we end up getting c is equal to n, which is integer, times pi minus x. And it is this that is the problem. Because in order for me to be able to find out a constant value that would make this work, I would have to plug in a specific value of x to do that. And by definition, this is not a constant solution if I have an independent variable in that particular expression. Okay. So because of that, we know that this particular ordinary differential equation that we're dealing with does not have any constant solutions in it. So that's an example of a first order ordinary differential equation that does not have a constant solution. That's the kind of stuff that you end up with whenever you try to solve for one. All right, so let's work this example live. So the first thing that we want to do is rearrange this particular differential equation to where we just have dy over dx is equal to. So first thing that we want to do is distribute here. So this would be plus 8y minus xy equals y squared minus 8x. And then of course, to get dy over dx by itself, I would subtract 8y to both sides, add xy to both sides. So I would have minus 8y here plus xy here plus y squared minus 8x. Now, now that we have this, what we want to do is try to figure out, well, what value of y here is going to allow this right-hand side to equal 0. Well, to do that, I see I have 4 terms here, so I can consider factor by grouping. I can kind of rearrange this so that whenever I do my grouping, it'll be a little bit easier to do. So I see that these 2 terms have an x in it, and these 2 terms have a y in it. So I'm going to rearrange them that way to see if that helps me out some. And let's see, I'll do this minus 8y here. And I'll say plus, and then we'll have xy minus 8x. And of course here I can factor out a y out of both of those terms. And here I can factor out an x out of both of those terms. And of course we see that inside the parenthesis we have y minus 8 being the same. So if we factor that out, y minus 8, then what we have left is a y plus x here. And so from here, if I want to know what my constant solutions are, I would have to consider when y minus 8 is equal to 0, okay? And the reason being is that, again, if I let y equal to some constant, then I know that the derivative with respect to x of this constant would have to be 0. But that also means that whatever value I plug in here, I would actually, this would have to make this whole right-hand side go to 0 as well. And of course, in this case, we know that y just ends up being 8. And so this would be our only constant solution that we have here, okay? Now, notice if I was to solve, if I was to say, let y plus x equal 0, if I had this, and then I say solve for that, I would have y equals minus x. This would be considered a non-constant solution to this differential equation, okay? But since I'm only worried about the constant solutions, I don't worry about that, okay? For the example that we're doing there. Now later on, we're actually going to be worried about actually having both the constant and non-constant solutions, but for right now, we're just worried about the constant ones. All right, so for our last example here, we want to do the same thing. We want to get this to look like dy over dx is equal to some function here. So do that, dy over dx. We divide both sides by x minus 2. And of course, this situation here, this is going to be a case where the differential equation is neither directly integrable nor autonomous. And to figure out what constant value here would satisfy this equation for a constant solution, all we do is just look at the numerator, okay? And of course, y equals -3 would be a constant function where if I was to take the derivative of it, derivative of -3 would be 0. And if I was to take -3 and plug it into here, it would be 0, okay? So this would be the only constant solution that we have to this particular differential equation, okay? Now, note that I did not look at the case when x minus 2 is equal to 0. I did not look at that. Part of the reason I didn't look at that is because I'm not trying to find out when I'm not trying to find out when my derivative does not exist. I'm not trying to find that, okay? If I wanted to know the values of x for where whatever my function y is, if it couldn't have a derivative, then I would look at when x minus 2 is equal to 0, okay? Or namely when x is equal to 2. But I'm just trying to find a constant value for to represent a function, so a constant function, so that when I plug it into here, I get 0, and when I actually take the derivative of that particular function, I'll also get 0. Okay, and we see that the function y equals -3 is the only one that satisfies that. So this concludes the video on first order differential equations and being able to recognize the directly integrable versus autonomous versus neither directly integrable or autonomous, as well as exercising our skill of being able to find constant solutions for these particular equations. So I hope this helped. Take care.